Alright guys, step into the future of architecture and engineering. We're exploring the top 15 most innovative construction techniques that are shaping the way we build. Let's start with number 15, a tuned mass damper. With increasingly restricted space in cities, developers are often looking at ways to build taller and taller structures. But with more floors a building has, the more engineering problems it faces, particularly in places like Taiwan, which is prone to high winds and earthquakes. That makes it all the more surprising that that's where you'll find Taipei 101, which was the first skyscraper in the world to be taller than half a kilometer and remains the 11th tallest building on Earth. At first, it seemed impossible to do, but the installation of a tuned mass damper within the building solved many of the issues, and this is a technique that's now common in most tall structures. Now, essentially, it's a mechanical device that's integrated within a structure to reduce the effects of mechanical vibrations, such as those from wind or seismic activity. The basic principle of a TMD is based on the mechanics of a harmonic frequency is designed to match a particular structural frequency of the building so that during events such as strong winds or earthquakes, when the building begins to resonate, this tuned mass damper is activated. As the building sways, the TMD moves in the opposite direction, and this counteracts the sway of the building, reducing strain on the structure. Amazingly, in the case of Taipei 101, which is located very close to a major fault line, the TMD is made from steel and weighs 728 tons. It cost about $4 million to build, and the pendulum is suspended between the 92nd and 88th floors, and it's so effective it's able to reduce movement in the building by as much as 40%. Number 14. Self-compacting concrete. So, self-compacting concrete, it's a highly fluid type of concrete that's able to spread into place. It fills gaps and spreads to the trickiest of areas, all without the need for mechanical vibration. Its development is one of the most important advances in concrete technology over the past few decades, and it's in the time and costs associated with traditional methods. The risk of human error is minimized, leading to more consistent and reliable results, and as vibration isn't required, the noise levels on construction sites are significantly reduced. It also looks better too, with the ability to create smooth surface finishes and intricate details that would be difficult to do with conventional concrete. And there are environmental benefits as well, as the amount of cement, which has a high carbon footprint, can often be reduced in favor of supplementary materials like fly ash, slag, or silica fume. There is, though, a reason why this isn't always used instead of traditional concrete, and that's mainly because it needs to be carefully handled and used to ensure it cures correctly. If this isn't done, it can turn out weaker than traditional concrete, which would defeat the purpose of using it in the first place. Number 13. 3D printing construction. So when you think of 3D printing, the small plastic printers that are notorious for going wrong probably come to mind. But the blueprint is a computer-generated design that's sliced into layers, guiding the printer to create the structure from the ground up. The device gradually builds the design layer by layer, and the type of concrete that's used is one that remains liquid as it's being put in place, but will be hard enough by the time the printer has begun the next layer so that more can be put on top of it. One of the major advantages of this 3D printing is its design flexibility. Now, unlike traditional construction methods, which are normally limited by the need for standard forms and molds, 3D printing allows architects and designers to create new complex shapes and custom designs without additional cost. It can also be much faster than other ways of building because automated printers can work around the clock. So by streamlining the construction process, buildings can be completed in a fraction of the time. This is a great way to minimize the disruption that's caused, but it also reduces the overall cost. Already, 3D printing has been used in some regions to create affordable housing solutions, with some companies having developed 3D printed homes that can be example is a highly effective insulating material that's known as frozen smoke because of its translucent appearance. And the fact that 99.8% of it is air, making it one of the lightest solid materials there is. It's made from a gel in which the liquid component has been replaced with gas. It has a porous structure with extremely low density and thermal conductivity, making it very good at insulating. For construction projects, this means that it offers a superior thermal performance in comparison to traditional fibrous or foam insulations. This means that a much thinner layer of the aerogel can provide the same level of insulation as a much thicker layer of another material. So not only can designs take this into account when deciding how thick the cavities and walls need to be, but it's also great for retrofitting older buildings where space for insulation is limited. Aerogel's low thermal conductivity is due to its structure, which is composed of tiny pockets of air trapped within a network of interconnected silica particles. These pockets significantly limit the three methods of heat transfer, but it shows how new materials can make such a difference in construction that once developments have been made to make it cheaper and easier to handle, it'll be a great tool to reduce energy usage. Number 11. Green roofs. Often, you'll see buildings that make as much use of the interior space as possible, but very little use of the space that's been created on the roof. Well, designers are increasingly taking these areas into account, as they can't be used to improve the overall look of the building, but the environment within it and energy usage too. Green roofs, as they're known, are roof coverings where vegetation is intentionally planted over a waterproofing membrane. Now, potentially covering the entire roof, they can be lightweight and self-sustaining with drought-resistant plants, or intensive with a wider variety of plants that require more maintenance. Now, structurally, the layers of a green roof typically include a waterproof membrane, a root barrier, a drainage system, a growing medium, and the plants themselves, ensuring that they don't compromise the integrity of the roof itself. The substrate and plants absorb water when it rains, which reduces runoff and lowers the risk of flooding. With further benefits such as improving biodiversity in urban environments and helping in the creation of so-called wildlife corridors, and improving in the mental well-being of those who use the building by providing a green space to use, there's a reason why they're becoming increasingly common around the world. Number 10. Electrokinetic soil stabilization. One of the most important parts of any construction project is to ensure the foundations are suitable for what's about to be built. But what if it isn't? Well, normally you'd expect that to mean that you'd have to find somewhere else for the project, or would need to come up with a different design for the structure. But there is a way to radically alter the composition of the ground to make it right. Electrokinetic soil stabilization is a sophisticated engineering technique that can do just this, especially in soil with a high clay content. The technique involves the insertion of electrodes into this dewatering, in effect, reduces what's known as the pore water pressure and increases the effective stress and shear strength of the soil, allowing it to withstand larger weights. The second effect is called electrophoresis, and this is where charged soil particles, such as those found in clay, move towards the electrodes that carry an opposite charge. This can result in a more uniform structure within the soil and may also cause electrolysis of any water remaining content, which will create gases that can help flush out contaminants. Electrokinetic soil stabilization, it's really useful in situations where traditional stabilization methods aren't possible, such as in areas with restricted access or where the soil's too wet or too weak for conventional machinery to operate. This makes it an attractive option for stabilizing soil beneath existing structures or in environmentally sensitive areas where minimal disturbance is required. Number 9. Japanese joinery. Japanese joinery is a historic art of creating joints that interlock the Japanese principles of simplicity, naturalness, and understated beauty, or wabi-sabi, and is why the country is so well known for its timeless wooden architecture, from residential homes to historic temples and shrines. In traditional Japanese construction, the wood is carefully selected for its quality, grain direction, and various other properties. Craftsmen, known as daiku, shape the wood into complex interlocking joints that give the resulting structure incredible strength and flexibility. This flexibility is critical in earthquake-prone Japan, where buildings need to be able to absorb and dissipate seismic energy. Joints such as the dovetail, mortise and tenon, and complex scarf joints are precisely cut to ensure a snug fit that becomes tighter over time. Each type of joint is designed for a specific purpose. Some provide structural support, others allow for movement, and some are simply for decorative purposes. For example, the kanawasugi joint, which is a type of scarf joint, is used to connect two pieces of wood end to end in such a way that it's nearly impossible to pull them apart. Some of the best examples of how effective. Number 8. Smart glass. Virtually every building you see makes use of glass, as it's a great way to let in natural light and to limit the number of bricks and other materials that are needed. There is, however, a better version called smart glass, and in places where it's affordable, it can make a huge difference. It's also known as switchable glass. Now, it essentially uses advanced technology to allow users to control the amount of light and heat passing through the glass with a simple flick of a switch. This makes it a game changer in modern buildings looking to promote energy efficiency while remaining comfortable and good to look at. Smart glass can be used for windows, skylights, and internal partitions. It usually makes use of electrochromic technology, which means the glass can change color when a low-voltage electric current is applied. When activated, ions move between layers of material within the glass and alters its thermal and optical properties. It can change from transparent to opaque, block out ultraviolet light, or filter heat from the sun. Modular construction. Modular construction is a process where buildings are constructed off-site under controlled conditions, using the same materials and designed to be the same standards as conventionally built facilities, but with the potential to be finished in about half the time. Buildings are produced in separate, smaller modules that are then transported and put together on site. Structurally, modular buildings are generally stronger than site-built ones because each module is engineered to independently withstand being transported and lifted onto foundations. Once together and sealed, the modules become one integrated wall, floor, or roof assembly. It's the speed at which they can be completed that's obviously the biggest appeal here, as projects can usually be completed 30 to 50% quicker than traditional construction. There's a potential cost benefit too, even though the cost of the modules themselves can sometimes be higher than a traditional construction. The shorter construction time can substantially reduce labor costs, and the early completion of the project means the build costs to escalate. It's not possible then in all scenarios, but in the ones that it is, it makes a huge difference to the viability of the project. Number 6. Shape memory alloys. Shape memory alloys are a class of materials that can return to a previously defined shape or size when subjected to a certain temperature. Now, this characteristic, which is known as the shape memory effect, happens because of changes in their crystalline structure that allows them to recover from deformations when heated above a certain transformation temperature. The most common types are nickel-titanium alloys, but others, including copper-aluminum-nickel and iron-manganese-silicon alloys, are also used across various industries. While still in the early stages, the application of shape memory alloys is changing the way that buildings and structures are designed, constructed, and maintained because of their potential to be used to create components that automatically adjust and repair themselves. They can, for example, be used to make rods or wires that are embedded within concrete or other building materials, be a way to add new functionality to buildings and support moving components. In large facilities or in structures such as stadiums with retractable roofs or bridges with movable sections, they could provide a low-energy, reliable mechanism for it to move without the need for a complex mechanical system. Number 5. Biomimetic design. Humans, well, we may be the most advanced species on the planet, but sometimes the best approach to build effective structures is to look at the animal kingdom and see how others do it. It's known as biomimetic design. It can often lead to more sustainable, efficient, and innovative design solutions, learning from animals that have evolved over millions of years to optimize their own process. One of the best examples of biomimetic construction is the Eastgate Center in Harare, Zimbabwe, which mimics the self-cooling mounds of African termites. Termites maintain a constant temperature inside their mounds despite extreme outside temperatures. In a similar way, the Eastgate Center features a passive cooling. Biomimetic design also gives technology like self-cleaning materials inspired by the lotus leaf. The leaf's microstructure allows it to repel dirt and water, keeping the surface clean without the need for chemical detergents. This concept has been applied to create self-cleaning windows and exterior panels, reducing maintenance costs and environmental impact. We are just at the beginning of what's possible in this field, though. Researchers are just now beginning to look at responsive systems found in nature, like the pine cone, which opens and closes its scales in response to humidity. Similarly, buildings can feature adaptive elements that respond to the changing weather conditions to optimize light, heat, or airflow, further enhancing energy efficiency and comfort. Number 4. Self-healing concrete. Concrete is, of course, one of the most widely used materials on a construction site around the world. It's easy to make and solidifies to be extremely tough. But there's a problem once it's in place. Over time, it may crack. And while at first this is a species of bacteria that can produce limestone. These bacteria, along with a calcium-rich nutrient source, are put in microscopic capsules or lightweight aggregates and are mixed into the concrete. When a crack forms, water enters and causes these capsules to open, which wakes the dormant bacteria. The bacteria then consume the nutrients, and in the presence of water and carbon dioxide from the air, they form calcite, which is a crystalline form of calcium carbonate, and seal the crack. The species of bacteria that's used are from the genus Bacillus because they've been found to be able to survive the high pH of concrete for long periods of time. Furthermore, these bacteria aren't dangerous and have no impact on the environment once they've been activated. The healing process starts as soon as the crack forms and continues until all the nutrient sources are consumed, and the result is an ingenious biological system that can enhance the durability and service life of concrete structures. This is really useful in hard-to-reach areas like underground pipes or tunnels, where manual technology that makes use of the constant temperatures of the earth to condition the temperature of air before it enters a building. This sustainable method of temperature regulation is becoming increasingly appealing. The construction industry and architects and builders seem energy-efficient alternatives to traditional heating, ventilation, and air conditioning systems. The basic concept behind this underground cooling tubes is simple. A series of pipes are buried at a certain depth where the soil temperature is relatively stable, and the air outside is then drawn through those pipes. As it passes through, it's naturally heated or cooled depending on the season, before being passed into the building. In summer, Earth's cooler temperatures can reduce the incoming air temperature, and in winter, it can increase it. For this to work properly, the depth at which these tubes are buried are critical. It must be deep enough to reach a point where the temperature remains constant, generally around 50 to 60 degrees Fahrenheit or about 10 to 16 degrees Celsius, depending on the local climate. A balance must be struck though. Longer tubes can increase resistance to airflow and may require additional energy to move air. Because of its fast-growing nature, bamboo has been used in some parts of the world for construction for thousands of years, and in modern times it's been seen as a much more sustainable alternative to conventional building materials. There's certainly no lack of supply, as some varieties can grow up to 3 feet or a meter in a single day and make it one of the fastest-growing plants on Earth. Unlike hardwood trees, which can take decades to mature, bamboo reaches full maturity and can be harvested within 3 to 5 years. This rapid growth cycle allows for much more frequent harvesting without damaging the ecosystem, and as an added benefit, bamboo absorbs carbon dioxide and releases 35% more oxygen compared to an equivalent mass of trees. Structurally, bamboo offers great strength and flexibility, which are crucial to construction purposes. Specifically, it's got higher strength-to-weight ratio than many timbers and is similar in tensile strength to steel. For construction, bamboo can be used in a variety of forms, such as whole bamboo poles, splint bamboo, bamboo fiber, a list. Number 1. Floating architecture. So, floating architecture is a concept that's been around for centuries, but with technological improvements, it's now much more possible than ever before. Essentially, it's when you build structures that float, and the increasing challenges posed by compact cities and rising sea levels due to climate change, architects and urban planners are turning to water as a new frontier for development. It is an adaptive architectural solution that offers a sustainable way to cope with flooding and create new living spaces, taking advantage of the underused surface area offered by lakes, rivers, and coastal waters. A major benefit of floating architecture is its resilience to flooding, and unlike traditional buildings, floating structures rise and fall with the water level, providing a built-in response to potential events. This makes them ideal for flood-prone areas or regions that experience significant tidal changes. In the Netherlands, for example, floating houses are part of the urban landscape, providing living spaces that are both practical and resistant to changing water levels.